Okay, so welcome back to particle physics and a standard model. This is lecture 15. So last time we ended with looking at rotations of quantum mechanical spinners in real space and saw that the spinners the rotation matrices that apply on these spinners live in SU2 space, right, and that is where we got the notion of the SU2 group, and from there we formally defined what a group was in terms of its properties, and then we saw some classifications of groups. We saw that you could have discrete groups, continuous groups and finite groups, and we saw that all discrete groups are finite groups and so on, right. And we just started looking at what we meant by representations of certain groups that are described with matrices, right. So we saw UN, ON, SUN, SON and so on, right, unitary and orthogonal groups, and we just started talking about representations. So we will explore that theme now, alright. So I was saying that for every group multiple representations are possible. So what do we mean by that? Okay, it is best illustrated if I start telling you what are the kinds of representations. So let us start with something trivial. In fact, it is called the trivial representation. So trivial representation is when you have every group element, okay, mapped to some constant, just let us just call it 1, okay. So you might wonder how this is a group actually. What if every element is mapped to just 1, the number 1, right? Well, it actually does form a group. If you just go back and see all the properties of a group, it does satisfy associativity, right, and inverse, identity and so on, right. So of course you can always represent the entire group with just the number 1. So that is called the trivial representation, and we do see examples of this in physics. What is this? This is what we would call a scalar, okay, of say some SO3 or SU2 and so on. In other words, this is a singlet of this group. It does nothing under transformations, but it nevertheless is an element of the group, and it is in fact it is a trivial representation of the entire group, okay. So the next not so hard thing to understand, not so hard to understand representation is the fundamental representation. Now I would say this is by far the most important representation of a group, okay. This is what we see again and again in nature, in particle states and so on, in the standard model especially, okay. So what is this? This is the group of matrices in say in SUN or whatever or ON that is representing itself basically. So you might wonder what this means. It just means if we take SU2 for instance, right, we use 2 by 2 matrices to rotate 2 by 1 column matrices, right, spinners basically, right. So because it was an SU2, the group of matrices that we wrote as A, B and so on, spinners that we wrote like this set represents itself now, right. So, that is indeed a fundamental representation. Okay. Now, this for an SU2 we saw that we used a 2 by 2 matrix, right. We used a 2 by 2 matrix to do the rotation on spinners like these. However, even here you could use higher dimensional matrices to represent lower dimensional groups. Okay. In other words, it is not at all crazy to have represented your spinners with say a 3 cross 1 matrix, okay, a 3 row matrix, basically a 3 row column matrix, and the rotations with, so let me call this rotation matrix. So, the rotations with basically a 3 by 3 matrix, it is completely possible, although it is an SU2. Okay. Why? All you need to do is satisfy the conditions of the group basically, right, and then satisfy the conditions of the unitarity of the matrix, like you need u dagger equals u dagger u equals 1 and so on, and SU2 has its own special conditions, like it needs to be generated by Pauli matrices and so on, which we will see. Each group has its own identity, has its own unique character. So, as long as we satisfy that, it does not matter what is the dimensionality of the matrices that we use to basically generate the group. Okay. What is the dimensionality of the matrices that constitute the group basically. Okay. So, I can represent an SU2 with a 7 cross 7 matrix if I want. Okay. So, higher dimensional representations are always possible, but these basically all constitute the fundamental representation. The matrices basically represent the group themselves. Okay. All right. And then there is the notion of an irreducible representation. This is also a very important concept. This is again something that we see again and again in the standard model. Okay. And this is what we will be mostly interested in as well. This just means I can have a matrix representation of the group, but I should not be able to decompose the matrix into block diagonal forms like this. Okay, that is if I have 0 0 0, right, this would make it this is a reducible representation. So, you can see why, right. If I have it in block diagonal form, then these matrices could act on column matrices such that up to a certain point you have a transformation, and then there is another part of the column matrix that undergoes another transformation from the other block diagonal part, right. If you have that, then you have basically broken the group into 2 bits, right. That is why it is called reducible. As long as you do not have that, as long as you only deal with one block, so that you cannot divide it into further blocks, that is an irreducible representation. All right. Okay. So, maybe I did not say this explicitly, but for fundamental representation some examples would be, can you think of some examples? In real space, if I have any vector, let us take any vector, okay, and I want to rotate it, then I apply SO3 matrices, right. So, vectors are basically 3D representations of SO3. What about 4 vectors? What group are they representations of? So, if you did not know before, so 4 vectors, right, they are on Minkowski space, right, but in group theory language they are on the SO1 comma 3 group. The 1 stands for the time dimension, 3 is for the space dimension. Okay, so 4 vectors are again or on the fundamental representation of the SO13 group. Okay, and along the way we will see that spinors in the quantum field theory sense are also fundamental irreducible representations of the Lorentz group, but in a non-trivial way. Okay, we will see how. Okay, now back to this. Have we seen some irreducible representation before? Some of the things that we just talked about are irreducible representations indeed. Okay. One other place we have actually already seen this is in the eightfold way. Remember from the first lecture we drew meson octets and baryon octets and so on, right. So, those constituted the eightfold way of Murray-Gell-Mann, right, Griffiths chapter 1 and 2, right. So, the eightfold way basically comes from the SU3 group basically that acts on 3 flavors, the 3 light flavors of quarks, UDS, okay. And it turns out that the SU3 can be represented in a way such that you can break it into 2 irreducible representations, one with dimension 1, the other with dimension 8 generators basically, okay. So, that is the reason why you had a meson octet, although it was an SU3 there are 3 flavors, you had an octet and then you also had a singlet. If you go back and look at the octet diagram, you will see there is also a singlet sitting around there, right. That comes basically from group theory. It comes from taking group and breaking it down into their irreducible representations. Okay, excellent. So, we will see all this. So, this is just an introduction. We will catch up with all this and we will actually use all this in glorious detail when we deal with the standard model. Okay, okay, good. Now, let us move on to yet another very important concept that makes use of group symmetries and so on. Okay. So, we just touched on the eightfold way, we saw there were some symmetries involving flavor. Let us take this one step further. Okay. So, this sub module, let me call it flavor symmetries, but I am going to put symmetries within quotes, okay, because these are not exact symmetries, unlike the gauge symmetries of the standard model, unlike some even global symmetries like baryon number and lepton number. Okay. So, let us begin with an observation that Heisenberg had made. Okay. I mean, we can also make this observation, but Heisenberg particularly saw something more in this, namely he observed that the mass of the neutron, okay, which I am writing up to 2 decimal places, is not particularly far off from the mass of the proton, correct. We usually just for many problems we just approximate these to like a GeV, right. But even if you do write down all the decimal places, you find that the difference in the masses is only about 1.3 MeV, compared to what their actual masses are, which is about 940 MeV, right. So, this made Heisenberg wonder whether the neutron, okay, or the neutron and proton, two spin like states of some single particle species, okay, which we can just call N to stand for nucleon. Okay. So, this is what Heisenberg wondered. In other words, he wondered whether it is possible at all to just write the proton and the neutron as some quantum superposition basically. Can you put them both on the same footing? Just like in spin, right, you would write a generic spinor as a superposition of an up and a down, right. The up and down refer to the Sz eigenstates, correct. So, he wondered whether you can do this for the proton and the neutron also. So, obviously there are some differences, there is a mass difference, the proton has an electric charge and the neutron does not have an electric charge. So, obviously you would say, yeah, maybe you can't just do this right away, but just go with this. Let us see if electric charge pops out of this exercise as a byproduct of being able to rotate between the proton and the neutron. Okay. If that were so, then since this looks very much like spin, right, I can write the proton in matrix notation. I can just write the proton this way and the neutron this way, correct, just like in spin. Remember, this is not spin, this is something like spin, right. I can always represent the proton and neutron this way. So, since this is like spin, Heisenberg called it isospin, okay, and the operator obviously you can denote with just capital I with the components in some isospin space, just like spin, right. Spin, the two components of the spin are not in real space, they live in their own spin space, correct. It is a Hilbert space, but in particular a subspace of that was the spin space, that is where the two spins were able to rotate into each other, correct. Similarly, for isospin, where proton and neutron are represented like spinors, you can have rotations in isospin space, okay. Let me just be clear, I am going to write it is not real space. It is always possible to do this if you think the proton and the neutron are part of the same thing, and you can rotate them into each other, right. Again, to take this analogy further, one can say that the nucleon N, right, carries isospin half, just like S is equal to half, right, and that I can once again all the algebra about I and I1, I2, I3 go through all the commutation relations, and then I can pick I3 or IZ if you want, but people just call it I3. I can pick I3 to be the other operator that I can measure simultaneously with the total I, just like in spin, okay. All the algebra exactly carries through. Then what would be the eigenvalues of I3? That would also be plus or minus half, correct, just like Sz. So, if that were the case, I can write the proton state in the usual spin notation. I can now assign the proton an I3 of half. So, this is I, this is I3, right, and then I can assign the neutron an I3 of minus half, because again this is I and this is I3. Okay. All right. So, this is the operator, right. If there were some interaction that is invariant, if there is a theory or an interaction invariant under this rotations in this space under the isospin operation, then there has to be a Noether charge, right, because obviously this is a continuous symmetry, right. The way we written it, it is all a continuous symmetry, just like angular momentum and spin angular momentum, correct. And that Noether charge okay is also called, no surprise, it is just isospin. Just like the Noether charge of the spin operator, we just called it spin. The conserved quantity here is also just isospin, okay, just like angular momentum. Let me just say it explicitly. Okay. So, it turns out that there is a Noether charge associated with at least one interaction that we know of, and that is the strong interaction. In other words, the strong interactions are indeed invariant under isospin rotations, let me call it that. It is not rotation in real space, okay, rotations in isospin space. Alright, this was Heisenberg's assertion. He took this as a starting point, and from that he was able to derive a lot of interesting consequences. What if the strong interaction is invariant under rotations of these states under in isospin space? Alright. So, if now that I have stated all this, can you guess what is the group under which these transformations happen from your experience with quantum spin? Of course, this also now has to be the SU2, correct. So, SU2 is again the internal meaning this is not a space time symmetry, this is all happening within the quantum states the way you defined it, right. So, SU2 again is the internal symmetry group. See, we keep seeing SU2 again and again, right. We saw it in spin, we are seeing it in isospin, we will see it a few more times. We will see it for the weak interaction, we will see it when we split the Lorentz group and so on, okay, because SU2 is a very simple group, it is one of the simplest unitary groups that you can write down, maybe the simplest, and it has a lot of interesting special properties, and nature seems to make use of it again and again in various settings, okay, that is what it is. And of course, I also have to specify that the nucleons, that is the neutron and the proton, belong to the 2D representation. So, that is trivial, right, we just wrote everything as 2D representations, okay, good. So, with this understanding, we can now see a bit more into what the whole eightfold wave was about, okay. So, the rows in the eightfold way, so let me just say in the baryon or meson octets and the baryon decuplet, right. These basically are isospin multiplets, just like the proton and the neutron belong to an isospin doublet, correct. Similarly, in the octets and the decuplet, each row corresponds to some isospin multiplet. So, this could be a triplet, it could be a quadruplet and so on, okay. And of course, each member corresponds to a separate value for I3, okay. Alright, so now you can go check this. So, I am going to write down a few examples of this, okay. Now, for example, for pions, how many pions are there? One neutral and two charged pions, correct. So, it turns out for pions they are on an isospin triplet, alright. So, I can write the pi plus in isospin space is basically 1 comma 1, the pi 0 is 1 comma 0 and the pi minus is 1 comma minus 1. See, just like spin. So, if the spin is 1, I have 3 possibilities for I3 and that is what I have written down, okay, and you assign I3 in this way, right. For the lambda baryon, it turns out there is no isospin, okay, it is an isospin singlet, and so I would just write 0 comma 0. So, you can go look this up again in the baryon decuplet, sorry, the baryon octet, okay. How about for the delta baryon? What is a delta baryon? What is it made of? It depends on which charge assignment we are looking at, which electric charge assignment, but it is made of basically u quarks and d quarks, okay. So, let me just write this. So, let me first write what delta baryon is and then I will write the isospins, okay. So, it turns out for delta baryon, if I have a doubly charged delta baryon, that is basically a u, and then a singly charged one, it is like the proton, it is a UUD, okay. You might wonder if a proton already has UUD, then why do we need another baryon with UUD? It can happen, and that is where isospin comes in, okay. And then I can have a neutral one which is a UDD, and finally a negatively charged one which is a DDD, okay. So, this should tell you, this should give you a clue as to what the isospin, what kind of isospin multiplet the delta baryons live on. So, can you guess what should it be, which one would take 4 values? Of course, that would be I equals 3/2 for the delta baryons, okay. And in the order in which I wrote them, so delta plus plus would correspond to an isospin of 3/2 comma 3/2, delta plus is again 3/2, but what do you think this should be? Demote it by 1, and of course delta 0 corresponds to 3/2 minus half, and finally delta minus is 3/2 minus 3/2, okay. So, in other words, the multiplicity is just like in spin, it is 2i plus 1, instead of 2s plus 1 you have 2i plus 1, good, clear, okay, very good. So, in the last 1 or 2 minutes, let me wrap up with an empirical formula, okay, that Gelman and Nishijima had noted, and in the next class we will pick that up and see some consequences of it. Okay. So, I have written down the isospin for pions. I have also written one for the lambda baryon, which contains an S quark, right. So, lambda baryon is basically a UDS. Okay. But some of these are mesons, some of these are pions, sorry, some of these are baryons, some of these contain the strange quark and so on, right. So, there seems to be some pattern among them, and this formula basically tells you exactly what that pattern is. Okay. So, this is Gelman, Nishijima formula tells you the exact relation between these various quantum numbers that we saw, and that is that the electric charge of a particle species is the I3, the third component of isospin. In fact, this is how you assign isospin also sometimes, plus half baryon number, okay, plus the strangeness. So, this is baryon number and this is strangeness. Okay. So, with this there is one systematic way in which you could assign I3 using this formula, okay, and that is to assign I3 equals I to the state with highest Q basically. Notice that is what we have done here, right. Delta plus plus we gave the highest I3 possible, which is the I itself 3/2, and then when I go back for the pion, the pi plus I gave I3 equals 1, right, and so on and so forth. And then even for the neutron and the proton, right, proton has the highest electric charge between these two, I gave it the highest value of I3, which is I, right. So, this is how you do the assignment, and in the next class we will see one consequence of this, and then we will also see another very neat consequence of the concept of isospin itself, okay, and from there on we will go on to construct the standard model. Okay. So, I will end here, thank you, see you next class.